Alright, so the next set of identities are known as the power-reducing identities. And really all they are is another way to look at the ones we were just using, well, one of the ones in particular that we were just using. You guys are familiar now with the double angle identity for cosine. Okay, so this is it in one form and in another. And if we rearrange each of those forms, we can obtain what's called the power-reducing identities, these two. Okay, and it's basically just using the same identity, but in this new form, if what you want to do is go from something with a larger power of sine or cosine to something with a smaller power, and you don't mind changing the argument from a single x to a multiple x, in this case 2. Okay, so as an example of using that, if we're asked to break down sine to the fourth of x into smaller powers of sine, actually what they want is only first power of cosine, and the argument can be anything it needs to be. Okay, so the first thing that I would do is say, look, I don't know anything about sine to the fourth, but I do know about sine squared. And what sine to the fourth is it's sine squared squared. Okay, so I'm just going to stick this identity in here for sine squared of x. So what I end up with is 1 minus cosine of 2x over 2, which is sine squared x, all squared. Now, if you want to square a fraction, you have to square the top and the bottom. And it might be easier if we think about this. It's the same thing to square something or to multiply it by itself, but I think it might be easier to see if we write it out like that. Whoops. Okay, we're squaring it, so we're multiplying it by itself. Well, the denominator is easy. We just multiply 2 by 2 to get 4. But what the heck is in the numerator? Well, we have two terms in each of these, so we're going to have to do FOIL to figure that out. 1 times 1, 1 times that times 1. We're going to end up with 2 of these. And we're going to get plus cosine squared of 2x. Okay? Notice that the arguments don't square. I don't have cosine squared of 4x squared. If I multiply this times itself, I just have that squared. Okay? Alright, so we're almost there. We're supposed to have cosine. We do, but we still have a cosine squared. So what are we going to do? Right, we can use this one. And then it's a little bit weird because we have 2x as the argument. If that freaks you out, you can think of this as y. If you don't need to do that, fine. But for some of us, and especially the first time we do this, that helps. So maybe just over here, what I'll do is I'll work out what is cosine squared of y. Well, if this is cosine squared of x, then all I have to do is replace the x with the y, and I'll have it. Cosine squared of y should then be 1 plus cosine of 2y over 2. Right? So I'm just going to replace it here, and the whole thing is going to end up being plus that all over 4. Yuck! Right, now we don't want a y in there. We made y up. We have to fix it. Y is 2x. So 2y is how many x? Right, 4x. So what we really have then is 1 minus 2 cosine of 2x plus 1 plus the cosine of 4x all over 2 all over 4. Whew. Now, 1 over 4, that's just a fourth. 2 cosine 2x over 4, the 2 over the 4 makes a half, minus 1 half cosine 2x. Okay? Well, what about this thing? If we didn't have the over 4, this would be 1 half plus cosine of 4x over 2. 1 half over 4 is 1/8. Cosine 4x over 2 over 4, 1/8 cosine of 4x. The 1/8 and the 1/4 can go together. 3/8 minus half cosine 2x plus 1/8 cosine 4x. Alright, that's nasty. That's an example of using the power reducing identities to take something that had a high power but an argument of just x, and turn it into something with no powers other than the first power of cosine. And to do that, we had to make the arguments be multiples of x and not just x. Alright, now we'll see another set of related identities. Alright, yet another set of trigonometric identities can be derived from the same place. We started with these double angle identities for cosine, created these power reducing identities. Now if we just take the square root of both sides, we end up here, right? With a plus and minus. That's going to cause us some trouble later, but it's not that bad. Now if I just play a little trick and say, look, y is 2x. Then here's a y, here's a y. And what's x? Well, it must be half of y, or y over 2. If y is 2x, x must be half of y. So we can rewrite it this way, and this is the half angle identity for sine. Sine of something over 2 is just plus or minus the square root of 1 minus cosine of that thing, divided by 2. And cosine looks very similar, but there's a plus in here. And if you take the ratio of those two, you get this, which is the half angle identity for tangent. Okay, so these are all very closely related. They all should probably be on your next cheat sheet. Let's solve an example. If we're asked to find an exact value for cosine of 5 pi over 8, like in example 5, well, we can recognize that that is half of 5 pi over 4, right? Well, why does that help me? Well, I know the sine and the cosine of 5 pi over 4. I know an exact value for it. It's one of our special angles. What quadrant is 5 pi over 4 in? Well, if it helps, think about 4 pi over 4. That's the same as pi, right? So if I go 45 degrees or pi over 4 beyond that, that's going to take me down here into quadrant 3, right? That's 5 pi over 4. So what are the sine and the cosine? Actually, all we need is the cosine. What's the cosine of that? Let's see. Cosine is like x, and I'm going to the left, so it must be minus root 2 over 2. Okay, so we're going to need that here in a minute. 5 pi over 4 is our y. So we're looking for 1 plus cosine of 5 pi over 4 over 2. And then the square root of that with a strange little plus or minus out front. Okay, so that's just 1 plus the negative root 2 over 2, which is cosine of 5 pi over 4, all over 2. Now this is a bit of a strain. 1 over 2 minus root 2 over 2 over 2 minus root 2 over 4. Right? Root 2 over 2 and then divided by 2 again, or multiplied by 1 over 2. Right? Okay. So we've got plus or minus. We still haven't resolved that. The square root of. Now we're going to give these guys the same denominator, these two fractions. 1/2 is 2/4 minus root 2 over 4. Okay, now that they have the same denominator, let's squish them together. 2 minus root 2, yes, we have a square root under a square root. We're going to have to live with it. Over 4. Now that they're in one fraction like that, we can say that this is plus or minus root 2 minus, no, plus or minus the root of 2 minus root 2 over 2. This 4 can finally come out and just be a 2. And this is it. Now we just have to pick the plus or the minus. How are we going to do this? Going back to the very beginning, cosine of 5 pi over 8. Well, what quadrant is that in? 4 pi over 8 would be what angle? Pi over 2, right? And so 5 pi over 8 must be a little bit more than that, so we must be in quadrant 2. In quadrant 2, should the cosine of 5 pi over 8 be positive or negative? It should be negative, so our final answer is minus the root of 2 minus root 2 over 2. Ay, 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 that's a lot of 2's. So that's how you use the half-angle identities. All right? So the next section is on something completely different. It's not really derivable from these examples that we've been using again and again.